Hello, today we're going to look at entropy and the second law of thermodynamics. We're going to start with two formulae derived in my video Thermodynamics A-Level Physics. The first is the ideal gas law, which says that PV equals nRT, where P is the pressure of the gas, V is the volume of the gas, N is the number of moles of the gas, R is the gas constant, and T is the temperature of the gas. And that is a formula that we're going to need extensively in this video. The second equation that we're going to use is essentially the first law of thermodynamics, du equals dq plus dw. And what that means is that the change in internal energy in the gas is equal to the amount of heat that you put into the gas plus the amount of work that you do to the gas. Both of these are in, so you heat it up and you put work in. If either of these are taken out, if you cool the gas down or if you take work out, then these become negative terms. And what this shows is that this is a measure of energy, this is a measure of heat, and this is a measure of work. And so heat is the same as work, work is the same as heat. And that's one way of expressing the first law of thermodynamics. Heat is work and work is heat. Let's now consider a gas in a container. And we're going to have a piston here, which means that it can move up and down and the gas is in the container. And we can move that piston up and down without the gas escaping from the sides. And what we're going to do is to apply a pressure P to that piston in order to push it down. And we're going to push the piston down by a distance dl. Now we know that pressure is defined as force over area. So it's the force divided by the area, which means that force is the same as pressure times area. So the force applied to this piston here is going to be the pressure times the area of the piston. The work done as we push down on the piston is the force times the distance. That's the definition of work. And that is, force is pressure times area, so that's pressure times area, times the distance, dl. But what is A times dl? What is the cross-sectional area times the distance? That's the volume by which you compress the gas. So that means that dw is equal to P times dV, where dV is the change in the volume of the gas. Now we need to make one small change to this formula, and that is to introduce a minus sign here. And the reason for that is that as the work increases, so the volume decreases. Right? As you do more work, you push down, the volume decreases. So to show that, to make sure that the signs are correct, we have to put a minus term here. What the minus term is saying is that the volume decreases as the work increases. We can also see that if there is no change in volume, then there is no work done. So that's an important principle. If the volume doesn't change, then there hasn't been no work in or work out. Now, if dw equals minus pdv, then we can rewrite the first law of thermodynamics like this. We can say that du is equal to dq minus pdv, because minus pdv is the same as a dw. And that's another formula that we will need extensively in this video. Now, internal energy of a gas, U, is a function of temperature and volume. You might wonder why it's not a function of temperature, volume and pressure, and the reason is that pressure is not an independent variable. Once you've defined temperature and volume, pressure is automatically defined by virtue of the ideal gas law. Once V and T are known, P must follow. So we can say that energy is a function of temperature and volume. Now, it is a fact of mathematics, and I'm not going to prove this, but this is that du is the derivative which we describe as a partial derivative, and that's why it's got a curly d, with respect to temperature, if you keep the volume constant times dt, plus the derivative of u with respect to volume, keeping the temperature constant times dv. In other words, we're saying the total derivative of the energy is equal to the derivative of the energy with respect to temperature, keeping the volume constant, plus the derivative of the energy with respect to volume, keeping the temperature constant. Now, at constant volume, dv is 0 because there is no change in volume, and so that whole term goes out. And so we've got constant volume, and at constant volume that means of course that dw is 0 because we said that above. If there's no change in volume, there's no change in work, and that means that du is equal to dq plus dw, but dw is 0, so du is equal to dq, and that means that du equals dq equals this term here, which is partial derivative with respect to temperature at constant volume times dt. And this term here is called the heat capacity at constant volume. And that gives rise to the formula that du equals dq equals cv dt. And we'll need that as we go through on this video. Now I'm going to define a new term. It's called enthalpy. And enthalpy is simply defined, it's used the letter H for enthalpy, not entropy. Enthalpy is equal to the internal energy plus the pressure times the volume. And we say that H is a function of temperature and pressure. Now we're going to use the first law of thermodynamics, which we showed was du is dq plus dw, which is the same as dq minus p dv. We've derived that before. I'll put a square around it to remind you. We've seen that earlier in the video. And if you rearrange this, you find that du plus p dv equals dq. And that means that du plus pv equals dq. I've simply taken the d terms out of these two terms here. Du plus pv equals dq. But u plus pv is h. And so we've derived that the differential with respect to enthalpy equals dq. Now, if h is a function of temperature and pressure, then once again we can use the partial derivative terms by saying that dh is the partial differential of h with respect to temperature at constant pressure plus the partial differential of enthalpy with respect to pressure at constant temperature. And that equals dq, because we just showed that dh equals dq. But at constant pressure, last time you remember we were at constant volume, if we now take constant pressure, then dp, the change in pressure, is 0 because pressure is constant. And so now this term goes out because that is just 0. And so for constant pressure we have that dh is equal to the partial differential of h with respect to t at constant pressure times dt. And this term here we call the heat capacity at constant pressure. And that of course equals dq because we've shown that dh equals dq. And so now we have a formula that says that dq, and I'll put a little p here to show that we're at constant pressure, is equal to the heat capacity at constant pressure dt. And that's a formula we'll need later as well. So just to remind you what we've just discovered, we've discovered that the heat capacity at constant pressure is the partial differential of enthalpy with respect to temperature at constant pressure, and that the heat capacity at constant volume is equal to the partial differential of the internal energy with respect to temperature at constant volume. Now you'll recall that we defined enthalpy as being the internal energy plus PV. We've defined that before. And once again you can use the partial differentials by saying that the partial differential with respect to T at constant pressure is equal to the partial differential with respect to temperature at constant pressure plus dPV with respect to temperature at constant pressure. But at constant pressure, this P term is obviously a constant. So this term here is the same as P dV by dt at constant pressure. Now, going back to the ideal gas law, we had that PV equals nRT. It was one of the formulae that we started this video with. And that means that dV by dt is equal to nR over P. And if for the moment we let n equals 1, n you remember is the number of moles of the gas, so let's keep it simple and have n equals 1, that means that P dV by dt equals R. And so this term here is R, that term there is R. And so this term, which is dH by dt at constant pressure, well, that is just the definition of heat capacity at constant pressure. So we now have that Cp, which is the heat capacity at constant pressure, is equal to this term here, which is du by dt at constant pressure, plus this term here, which we've just shown is equal to R. And it would be nice to think that this term was the heat capacity at constant volume. But actually it isn't. It's du by dt at constant pressure, whereas the heat capacity at constant volume is du by dt at constant volume. So we're not quite there. But we're going to do a little trick, which is called the chain rule. And the chain rule says that you can expand du by dt, these should be partials of course, at constant pressure, that equals du by dt at constant volume plus du by dV at constant temperature times dV by dt at constant pressure. That is called the chain rule, and that's a well-established mathematical term. Now here's the trick. At constant temperature, we have said that there is no change in energy. Energy, remember, is the internal energy of a gas is what gives rise to temperature in the first place. Effectively, temperature is just a measure of the total energy of the gas. As the energy increases, the temperature increases. As the temperature falls, so the energy falls. So if you are at constant temperature, there is no change in energy, which means that du must be 0. And that means that this whole term becomes 0 because there's no change in energy at constant temperature. And that gives rise to the fact that du by dt at constant pressure is equal to du by dt at constant volume. And this is indeed the heat capacity at constant volume. And so now this term, which is this term, is equal to that term. And so you really have now derived that the heat capacity at constant pressure is equal to the heat capacity at constant volume plus the ideal gas constant. So just to recap, we have shown that the change in energy is equal to dq plus dw. That's the first law of thermodynamics. But that is equal to dq minus pdv. We showed that earlier in the video. And we've also shown that du is equal to the heat capacity at constant volume dt. So all of those things have been shown in this video. Now I want to look at a particular type of change of conditions of a gas. It's called adiabatic. Adiabatic means that in the system in which the gas is, no heat goes in, no heat comes out. In other words, you do the experiment inside an insulated case. So there is no heat passing through the barriers. All the heat stays within the system itself. And if there is no heat going in or out, then dq is 0. And that's called adiabatic. Another type of change, which we're not looking at the moment, is called isothermal. Isothermal means the whole thing is done at constant temperature, usually at room temperature, because that's the easiest thing to maintain. And generally you have to go slowly so that all the temperatures can even out to room temperature. That's isothermal. We're going to consider adiabatic, which means no heat in, no heat out. And we know from the ideal gas law that PV equals, nR, where R is the gas constant times T. We took that was the first formula we took in our video. And if you rearrange that, you get that P is equal to nRT over V. So now I'm going to substitute this term for P into this term here. So now we're going to get that du is equal to, well, dq is 0 because it's adiabatic. So it's simply minus pdv, and that's minus nRT over V, that's the P, times dV. But that equals the heat capacity at constant volume times dt, that's this term here. So we can rearrange this formula to say that Cv dt divided by T, that's this term divided by that term, is equal to minus nR dV over V. Let's once again set n equal to 1, so we don't have to worry about n equal to 1. And now we're going to integrate both terms. And that means we will get that Cv times the integral from the starting temperature to the final temperature, T1 to T2, of dt over T, that's this term here, is equal to minus R, because we've set n equal to 1, times the integral from the starting volume V1 to the end volume V2, dV over V. And you should know that the integral of dx over x is the log of x. So in this case, when we work that through, we get Cv times the log of T2 over T1 equals minus R times the log of V2 over V1. And you should know that mathematically minus the log of V2 over V1 is equal to plus the log of V1 over V2. And consequently, this term here, Cv log of T2 over T1, equals not minus R log V2 over V1, but plus R log V1 over V2. What you can also do is to take the term in front of the log and put it up as the exponent. They are the same thing, that's what logs do. So now we have that the log of T2 over T1 all to the power Cv is equal to the log of V1 over V2 all to the power R. And if that's the case, then obviously these terms here must equal these terms here. And what you can do is you can take the root of Cv on both sides and that leaves you with T2 over T1 is equal to V1 over V2 to the power R over CV, because we've taken the CV root, as it were, on both sides. So that goes down to 1, and this goes down to R over CV. And we'll need that later, so I'll put a box around it. So now let's go back to the term we derived just a little while ago, which says that Cp, the heat capacity at constant pressure, is equal to the heat capacity at constant volume plus R. That was also a term which we derived a little while ago. Well, you can see that if that's the case, just rearrange R is equal to Cp minus Cv, and that means that R over Cv, which we want because that's this term here, this is why we're doing this, R over Cv is equal to Cp minus Cv over Cv, and that equals Cp over Cv minus 1. And let's call this term here Cp over Cv. We'll call that gamma, just to save a bit of space. So R over Cv is gamma minus 1. So we can rewrite this formula here as T2 over T1 equals V1 over V2 to the power gamma minus 1. But we also remember from the ideal gas law that PV equals nRT, and therefore if again you let n equal 1, you will get T equals PV over R, and we're going to substitute that for the temperatures that we had in the formula we just derived. And so now you get that V1 over V2 to the gamma minus 1, which was actually the term on the right hand side of the equation we just derived, is equal to T2 over T1. Well, T2 is P2 V2 over R divided by T1, which is P1 V1 over R. The R's are going to cancel, and the V2 over V1 is going to actually reduce this term by 1. If you take V2 over here and V1 over here, you just get V1 over V2 to the power gamma. So what you end up with is, V1 over V2 to the power gamma is equal to, well, the R's have gone, the V2 and the V1 has gone, so that's now just P2 over P1. And if we multiply that out, top and bottom, what you get is that P1 V1 to the gamma is equal to P2 V2 to the gamma. In other words, PV to the gamma is a constant. Now you might say, hang on a minute, I thought Boyle's law says that PV was a constant. Why is it PV to the gamma? Well, Boyle's law, don't forget, does indeed say that pressure times volume is a constant, but only if the temperature is constant. Here we are talking about an adiabatic change, which means no heat in and no heat out, but there may well be a temperature change. And so for an adiabatic change, where temperature is not necessarily constant, it's PV to the gamma that is a constant for an adiabatic change. We're now going to move on to a new idea. We know from the first law of thermodynamics, let's put a line under that, we know that from the first law that du, the change in energy, is equal to dq plus dw, heat plus work. So the question is, can you take heat and convert it directly and efficiently at 100% level into work? Can you take some heat and can you make work out of it? And what Carnot discovered was that you couldn't. In other words, he tried to set up a system whereby you have a heat bath at temperature T1, and let's say that's hot. So there's a large source of heat in this bath. And what he wanted to do was to take heat out of it, say Q1 worth of heat, put it into some kind of engine, we don't know what, and convert that into work or convert that into useful energy. And what he wanted to know is, could he take the heat out of this plentiful supply of heat, put it into some kind of engine and generate work at 100% efficiency level? And he found that you couldn't do it on a continuous basis. The only way you could get this to work is if you had the hot supply, you took heat out of it, Q1, into some kind of engine which delivered work. So far so good, but there was always some spare heat which was lost, and that had to go to a cold chamber, temperature T2, which is cold. And only if you had an arrangement like that could you have an engine which delivered work. In other words, the system was not 100% efficient. Well, how efficient is it? Well, we can see that the work that you get out of this engine is equal to Q1 minus Q2. In other words, it's the difference between the heat that goes into the engine and the heat that comes out. The difference is converted into work. And the definition of efficiency is essentially what comes out divided by what goes in. Well, what comes out is work, and what goes in is Q1. Q1 goes into the engine, work comes out. So the efficiency is W over Q1. Well, W over Q1, W is Q1 minus Q2, and Q1 is Q1, and so you end up with the efficiency being 1 minus Q2 over Q1. Now remember, of course, that Q2 is smaller than Q1 because Q2 is what's left over after the work has been taken out. So Q2 over Q1 is going to be a fraction that is less than 1 and positive. So the efficiency is going to be 1 minus a fraction, which means it's going to be less than 100%. So the efficiency of an engine which converts heat into work must always be less than 100%, because otherwise the engine won't work. And that was a crucial piece of work that Carnot discovered. Carnot went on to develop what is often called the Carnot engine, or sometimes the Carnot cycle. Basically it involves taking the gas that we had before with a piston, so the piston can slide up or down, either compressing or expanding the gas. And what you do is you change the gas, sometimes adiabatically, which means no heat in or out, and sometimes isothermally, which means the temperature doesn't change. Now, if you are going to change it adiabatically, with no heat in or no heat out, then you have to do work, because that's the only way you can change it. In other words, you take hold of this plunger here, and you push it in, and if you push it in, the volume will go down, or you pull it out, and the volume will increase. Both of those are adiabatic changes, because no heat has gone in, and no heat has come out. On the other hand, if you want to do it isothermally, then what you have to do is to put a candle underneath, or a Bunsen burner or something. And you might think, but you're going to change the temperature. No, that's not true. You're putting heat in, but that heat will cause the gas to expand. But the temperature, if you do it slowly enough, will stay the same. So heat in results in increased volume, which means you get work out. So all the heat is converted into work, and no temperature change happens. Now you might say, hang on a minute, we just discovered that you can't convert all the heat into work. And the answer is no. What we discovered is you can't do it in the form of an engine. You can always get a one-off change from expanding the gas, but you can never do that again without cooling the gas, and that means you've got to take heat out. So for a one-off expansion, you can indeed convert all the heat in into work out and leave the temperature of the gas, because the energy doesn't change, so the temperature of the gas doesn't change. And that's the way you do it isothermally. So here's the graph. It's a PV graph. This is pressure, this is volume. And what we're going to do is to simply take this gas, and we're either going to expand the gas or contract the gas isothermally or adiabatically. So let's start off with a pressure and a volume here. And what we're going to do is to move the gas isothermally to a new pressure and a new volume. And because it's isothermal, of course, it must stay at a constant temperature. And the way you do that is you put a certain amount of heat in order to expand the gas. Remember, the gas volume is going to expand if you put heat in. And that's exactly what happens. The volume expands from here to here. The next stage of this cycle is to change the volume again. It's another increase in volume, but this time it's adiabatic, which means no heat in, no heat out. So in order to do that, you have to take the piston and move it up, and that expands the gas still further. But of course the temperature will now change. There's no heat in, but the temperature will change. And we've now gone to temperature T2. The third stage is to contract the gas from V back to here, and we do that isothermally at temperature T2. And to contract the gas, you obviously have to take heat out. So we take Q2 of heat out, and we get back to this point here. And then finally we go back to the point we started at, and that's another adiabatic change, which means no heat in, no heat out, but the temperature changes from T2 to T1. And when you get back to here, you're back at the same energy as you were before, so you're back at the same temperature that you were before. And that is called a Carnot cycle. It's an isothermal change, or an isothermal expansion, an adiabatic expansion, an isothermal contraction, an adiabatic contraction, back to where you started. So you'll notice if we label these points A, B, C and D, that the only time heat goes in or comes out, heat goes in when you go from A to B, and heat comes out when you go from C to D. No heat in or out here or here, because those are both adiabatic changes, and adiabatic means no heat in or out. You'll also notice that when heat goes in, the volume increases, which is not unsurprising. You heat the gas, its volume increases. When heat comes out, the volume contracts. So this is an engine. You can keep going round this cycle as many times as you like. And you'll be putting some work in and taking some work out. You'll be putting some heat in and you'll be getting some heat out. But what we've shown is that the maximum efficiency that you can get from an engine is 1 minus Q2 over Q1, where Q2 is the heat out and Q1 is the heat in. That's the maximum efficiency. You can never get 100% efficiency. Now let's go back to our formula that we derived earlier, which derived from the first law of thermodynamics, du equals dq minus pdv. Since when you go round this cycle, when you get back to where you started from, there is no change in temperature. You get back to T1. So there's no change in energy. So around one complete cycle, du is 0. There's no change in energy in one cycle. And that means that dq equals p dv. Now once again, the ideal gas law tells us that PV equals nRT, which means that P is equal to nRT over V, and we can substitute that P in here. So now we get that dq is equal to nRT over V dV. So now we can integrate that to find the values of Q1 and Q2. Now just let's remind ourselves that Q1 resulted in a volume increase from VA to VB. So if we want Q1, that's going to be the integral from VA to VB of nRT dV over V. If we want Q2, well, remember that Q2 was heat out, and that resulted in a volume change from Vc to Vd. So Q2 is going to be the integral of Vc to Vd of nRT dV by V. And once again, to keep the signs correct, since this is heat in, if this is heat out, then we need a minus sign to show that Q2 is heat out, where Q1 is heat in. Well, if we do the integral, we will find that Q1 is equal to nRT times the log of VB over VA. Sorry, that should be Q1. And Q2 is going to be equal to minus nRT times the log of Vd over Vc. But as I've already said, minus log Vd over Vc is plus log Vc over Vd. Q2 is equal to plus nRT log Vc over Vd. We did that earlier. And then, as we've said right the way back up here, efficiency is equal to 1 minus Q2 over Q1. We now have terms for Q2 and Q1. So let's write that. The efficiency is equal to 1 minus Q2, which is nRT log Vc over Vd, divided by Q1, which is nRT log VB over VA. And as you can see, nRTs cancel out. Oops, I've made a mistake there, of course. Let me just go back. When we integrate, we should have said, of course, that Q1 is equal to nRT1, because that's the temperature at which this takes place. And the temperature at which the Q2 comes out is T2. So when we get down to here, Q1 is nRT1 times this log, Q2 is minus nRT2 times this log, and that's T2 is there as well. So I shouldn't have cancelled these out, of course. This is T2 over T1. These are not cancelled. The two temperature terms are not cancelled. So let me write that out. That's 1 minus T2 log Vc over Vd divided by T1 log VB over VA. Whoops, over VA. And I am going to show in a moment that this term here equals 1, which means that the efficiency is 1 minus T2 over T1. So now let's show that this term equals 1. Well, earlier on in this video we showed that T2 over T1 is equal to V1 over V2 to the gamma minus 1, where gamma, you remember, was Cp over Cv. Well, I'm going to let gamma minus 1 equal alpha, again just for simplicity. And so multiplying out, you get that T2 V2 to the alpha is equal to T1 V1 to the alpha, which means that TV to the alpha is a constant. And that's for, remember, the adiabatic change from B to C and from D to A in the Carnot cycle. So let's just redraw that Carnot cycle so you can see what's happening. This is a pressure volume chart, and we went from A to B to C to D and back to A again, and we keep going around that cycle. And it was these two arms were the adiabatic changes, these two were the isothermal changes. And so for the adiabatic changes, this is valid. This occurred at temperature T1, this occurred at temperature T2, and so now you can say that T1 times the volume at B to the alpha is equal to T2 times the volume at C to the alpha. You can also say that T2 times the volume at D to the alpha is equal to T1 times the volume at A to the alpha. Now, if you divide the two T1 terms, you get T1 VB to the alpha over T1 VA to the alpha is equal to, divide the two T terms, divide the two T2 terms, T2 VC to the alpha divided by T2 VD to the alpha. Well, the T1s cancel, and now you get that VB over VA to the alpha is equal to VC over VD to the alpha. And that obviously means that VB over VA equals VC over VD. And if you look at the formula, in fact I'll just put it back up on the screen so that you can see it, that we had before, we had the log of VC over VD divided by the log of VB over VA. Well, VB over VA equals VC over VD, so those two terms are the same, so this is indeed equal to 1. So, now we've managed to show that the efficiency of an engine is equal to 1 minus Q2 over Q1, that is the heat out divided by the heat in, but we just showed that it's also equal to 1 minus T2 over T1. And if that's the case, then this term must equal that term. T2 over T1 equals Q2 over Q1. And if you rearrange that, you get that Q2 divided by T2 is equal to Q1 over T1. Q over T is a constant. And I am going to give that value of Q over T, that constant value, I am going to give that a name. I'm going to call it entropy. And entropy is usually denoted with the letter S, so S is Q over T, or you sometimes write it as the change in entropy is equal to the change in heat divided by T. Now, we defined efficiency as the work out divided by the heat in, work divided by Q1. And we've just shown that that is the same as 1 minus T2 over T1. And from that you can see that work is equal to Q1 into 1 minus T2 over T1. Now here's the point. This is the maximum efficiency you're ever going to get, and it will never be 100% because it's always 1 minus this fraction. T2 is less than T1, so this is a fraction, a positive fraction less than 1, so 1 minus a positive fraction less than 1 is going to be less than 100%. So we know the efficiency is never going to be 100%, and this is the maximum efficiency that you can get. But that's assuming you can get the maximum. We can't always get the maximum efficiency. So if you get not the maximum efficiency, then you end up with this equation that the work is not equal to this, but it's less than or equal to what Q1 into 1 minus T2 over T1. If you've got the maximum efficiency, which will never be 100%, then W will equal this term. But if for some reason you're not even getting the maximum efficiency, then W will be less than this term. Now you'll recall that we showed that W is equal to Q1 minus Q2. In other words, the heat in minus the heat out. Heat comes into the engine, that's Q1. Some of it goes out, that's Q2. The difference is converted into work. And so that is going to be less than Q1 into 1 minus T2 over T1. Obviously this Q1 here will cancel that Q1 term there, leaving minus Q2 equals minus Q1 T2 over T1. So let's just write that out. Minus Q2 is going to be less than or equal to, these two Q1s have gone, so now it's just Q2 times T2 over T1, and that's minus Q1 T2 over T1. And if you rearrange this equation, you will get that plus Q2 over T2 is greater than or equal to plus Q1 over T1. This equation here just rearranges into this. But look, Q2 over T2 is what I defined as entropy. That's the entropy at the end of the process, right? That's the heat out. This is the heat in. So S2 is greater than or equal to S1. And that is actually the second law of thermodynamics, that entropy always increases. The entropy at the end of the process is greater than the entropy that you put in. The entropy of what comes out is greater than the entropy of what goes in. Entropy always increases. Or to be more accurate, entropy never decreases. It can stay the same provided that the engine you use, which of course will never be 100% efficient, operates at its maximum theoretical efficiency. And since engines don't do that, if they did, the entropy would be the same. But if they don't, then the entropy will increase. What is entropy? Well, it's the measure of disorder. Or if you like, it's a measure of the usefulness of the energy that's around. For example, suppose you were to go on the beach and you make a nice sandcastle. That's a very ordered system. And then you go away and the tide comes in. What happens when the tide goes out? The sandcastle has been knocked flat, and you now have the same sand. The sand has not gone anywhere, but it is in a total state of disorder. Now, you never get a situation whereby the tide comes in on a flat sand, and when it goes out again, it leaves a castle. That never happens. You never get disorder creating into order. You might say, but you made the sandcastle in the first place. Well, yes, you did, but you used an awful lot of energy doing it, and the total entropy has increased. And what this means from the world point of view is that at the Big Bang, when the universe started, there was a low state of entropy and a high degree of order in the universe, a high degree of useful energy. And what happens over time is that entropy increases, so entropy of the universe is now higher, which means we have a greater state of disorder, and that means we have less useful energy. Think about it, food contains useful energy. We eat the food, that food is converted into energy which we use. Energy is never created or destroyed, so it's still around, but where is it? It's just lost into the ether. When you light a fire, you release the energy of the gas or the coal. That energy heats the room for a while, but then the heat dissipates. It isn't lost, it's still around, but it's out there in the atmosphere, not doing anybody any good. It's really, entropy is a kind of a measure of the usefulness of the energy that's around. It's the state of order, the state of potential. And as time goes by, the entropy of the universe increases, the state of disorder increases, the state of usefulness of the energy that's around decreases. And ultimately, of course, one can look forward to a universe with loads of energy, but none of it of any use. It will just be a dark universe where nothing happens, because all of the energy has dissipated into a form of disorder. Now, we can say, therefore, that the change in entropy is equal to the change in heat divided by temperature. And we've shown earlier in the video that that is one and the same thing as nR times the log of V2 over V1, where V2 is the volume at the end of the process of the gas, and V1 is the volume of the gas at the beginning of the process. So let's suppose we take a system, this is a PV graph, where we simply double the volume. So we go from here to here as part of our Carnot cycle. This is, sorry, no, you didn't see that. The volume has doubled, basically. We've gone from here, A to B, by doubling the volume. So if we've got a gas with a piston, then we will simply mean that the piston moves up and you've got twice the volume of gas that you had before. Well, if that's the case, we can take this formula here and we can say that delta S is equal to nR times the logarithm of 2V over V, because the volume has doubled. So whatever the volume was, it's now 2V, which is nR times the log of 2. Now, nR, which is the number of moles times the gas constant, is the same as capital N, which is the number of atoms or number of molecules, times Boltzmann's constant K. This is the number of moles. Each mole has a certain number of atoms or molecules, and so the gas constant and Boltzmann constant are just related in this way. So you can rewrite that the change in entropy is equal to the number of atoms or molecules times Boltzmann's constant times the log of 2. And that can be written as Boltzmann constant times the log of 2 to the power n. And 2 to the power n is essentially the number of what's called microstates, the number of different permutations that those atoms or molecules can have. And that gives rise to a famous formula, delta S is K log W, or you'll sometimes see it written K log omega, where W or omega are essentially 2 to the power n, the number of microstates that there are in the system. And this is known as Boltzmann's formula. He was very proud of that formula, and it is in fact carved on his tombstone. Well, this is all very theoretical and all very interesting, but does it mean we can tell anything from it? Well, let's just do a little experiment, or at least try to do an experiment. What we're going to do is to take a heat source. It's a hot source, it's temperature T1, and we're going to let some of the heat escape. We're not putting it through an engine this time, to a cold source. So all that's happening is that we're going to move a quantity of heat, Q, from a hot source to a cold source. You can think of that as you've got a warm house. This is the house, this is the outside. You open the door and heat goes out. That's why you don't open the door, because you don't want the heat to go out. Question is, why doesn't heat come from the outside in? Well, that's what we're going to discover. The total change in entropy, we've shown, must always increase. It could stay the same, but most of the time it increases because you never have perfection in terms of efficiency. And that means that the total change in entropy is going to be equal to the sum of all the changes of Q over T. Now, in the case of this system here, you've got Q coming out and Q going in. So the total change of entropy is going to be equal to Q coming out over T1 plus Q going in over T2. But remember, this is coming out, this is going in. So if it's coming out, you have to make it a minus sign. So delta S is minus Q over T1 to show that the heat's coming out, plus Q over T2 to show that heat's going in. And that is greater than 0, because you can show that if T1 is greater than T2, which it is because we're going from hot to cold, that Q over T1 is a fraction which is, Q over T2 is a fraction which is bigger than Q over T1. And therefore this term minus this term is going to be greater than 0. And that's okay, because entropy increases. And therefore heat will move from hot to cold. But let's try it the other way round. Let's now take our hot bath and our cold bath, as we did before. But let's say, can we now move heat Q from cold to hot? Well, once again, delta S is going to be the sum of all the changes of Q over T. And that's going to be minus Q over T2, because that's coming out of T2, plus Q over T1. And if T1 is greater than T2, which it is because T1 is hot and T2 is cold, then you can show that that is always going to be less than 0. But entropy is never allowed to be less than 0. And that's why heat cannot pass from cold to hot. And that's another formulation of the second law of thermodynamics. Heat won't pass from the cooler to the hotter. Or more accurately, heat cannot of itself pass from one body to a hotter body. Of course, a refrigerator does precisely that. It takes heat away from a cooler body and sends it out into a warmer room. But the only way it can do that is with an engine. And in fact, the overall entropy increases, even though on the face of it, within the fridge, the entropy decreases. It is more than matched by the energy that is wasted in the room. And finally, I just want to take the concept of entropy to show what happens spontaneously. Let's take a container with a partition, and on this side of the partition I'm going to have a gas, and on this side of the partition I'm going to have a vacuum. If you take the partition away, what will happen is the gas will simply expand to fill the whole of the container. It worked that way round, but it never works that way round. You never get a gas-filled container that suddenly has all the gas on the left-hand side and a vacuum on the right-hand side. Why not? Well, we're now in a position to answer. We know from the first law that du, change in energy, is heat in plus work in. And we know that the change in entropy is always greater or equal to dq over t. And that means that dq is less than t ds. Remember that ds will equal dq over t only if your engine is working at its maximum theoretical efficiency, which will always be less than 100%. But if it doesn't operate at the maximum theoretical efficiency, then entropy will always increase, so ds will always be greater than dq over t. And so dq is going to be less than, or of course equal to, we must always recognise that as a possibility, tds. Now we know, because we've shown earlier in this video, that you can also write the first law as du equals dq minus p dv. And rearranging this, you get that dq equals du plus p dv. But dq is always less than or equal to tds. So dq is less than or equal to tds. And if you rearrange that formula, you get that 0 is greater than du plus p dv minus t ds. And when that condition pertains, spontaneous action will happen. If that condition is not satisfied, things will not happen spontaneously. So the answer is that the reason that this moving to this happens spontaneously is because this formula here is satisfied. But the reason why this never moves back in this direction is because that formula is not satisfied. This is the formula for spontaneous action. If this is true, then things will happen spontaneously without any further assistance.